So how does an AI actually get smarter when, well, there are literally no more humans left to teach it? It's a massive, massive question right now. We're rapidly approaching a point where human annotated data is running dry. AI models are going to have to rely on self-evolution just to keep improving. But how do you stop an AI from learning the wrong things or, just repeating the exact same simple tasks over and over again? Welcome to this explainer. Today, we're diving into a really groundbreaking paper from researchers at Alibaba and their academic partners that attempts to answer exactly that question. They've introduced this fascinating framework they call skill self-play, and it completely rethinks how large language models, or LLMs, actually teach themselves. Here's our quick roadmap for today. 1. The AI training dilemma. 2. Introducing skill self-play. 3. Proposer, solver, and controller. 4. Evolving the skill library. And 5. Pushing the performance frontier. Let's get right into it.
Starting with Section 1, the AI training dilemma and the limitations of current self-improvement methods.
Right now, researchers generally have two pretty flawed options. It's a classic Goldilocks problem. The first is environment-bound self-play. Think of this like a basketball player just practicing free throws all day long. Sure, it gives very precise, reliable feedback, but it confines the learning to super narrow, rigid domains. The AI never actually learns to play the whole game. The second option is unguided generation. This broadens things out, but it relies on passive post-hoc filtering, basically just trying to weed out bad data after the fact. It's like playing a totally chaotic game with no rules. It leads to misleading noise, poorly framed tasks, and sometimes the AI's training data can literally collapse into total nonsense. Which brings us to Section 2, introducing skill self-play as a dynamic, co-evolving middle ground. Since neither of those first two options is just right, we get to the core innovation of this paper, skill self-play. Now, to really grasp this dynamic middle ground, we first need to define what a skill actually is in this context. A skill here isn't just a simple label. It's a reusable, modular block of procedural knowledge. Basically, it bundles task-specific instructions, rules, and executable validators all into one really neat package. Think of it like a highly adaptable coach armed with a playbook that constantly evolves based on exactly what the team needs to practice that day.
Notice how this evolving skill library proactively guides task generation. Instead of just letting the AI generate totally random tasks and then trying to passively filter out the garbage later, which, again, is what unguided methods do, skill self-play injects structural guidance before synthesis and explicitly verifies it afterwards. So it completely avoids the trap of passive filtering. And this is a huge deal because it means the AI is constantly, reliably generating high-quality, verifiable training data for itself. Moving right along to Section 3, Proposer, Solver, and Controller, our cast of characters. To make this incredibly technical architecture a bit easier to digest, let's personify it. First up, we have the proposer. You can think of the proposer as the teacher. Its entire job is to synthesize targeted challenges. But it doesn't just pull these out of thin air. It's strictly guided by those routed skill packages from the library. It crafts very specific, verifiable tests based on exactly what the current curriculum demands. Next, we've got the solver. This is our student. The solver's main goal is to step up and successfully resolve the tasks that the proposer just generated. By continuously taking these tests, the solver learns to execute complex logic, pushing its own capability boundaries further and further out. This is the core brain getting smarter with every single iteration. And finally, we have the skill controller. If the proposer is the teacher and the solver is the student, well, the controller is the principal. It stands back, analyzes the execution trajectories, and dynamically manages that skill library. It decides exactly which skills need updating based on how the student is performing. This kind of oversight is absolutely critical. It ensures the AI isn't just blindly learning, but learning the right things efficiently, without getting stuck in a rut. Section 4, Evolving the skill library and orchestrating this continuous co-evolutionary loop. So, how do these three characters actually orchestrate a progressively harder curriculum? They operate in a continuous co-evolutionary loop. Step 1, the system samples a skill from the library. Step 2, the proposer uses that skill to build a structured task. Step 3, the solver steps up and attempts to solve it. And Step 4, the controller evaluates whether it was a success or a failure and updates the library accordingly.
This tight loop is the real magic ingredient. It beautifully bridges the gap between structured verification and open-ended exploration, which allows the whole system to literally spiral upwards in intelligence. The really crucial point here is where this learning actually happens. Researchers call the peak of the curve the learning frontier, and skills self-play targets this exact sweet spot. If tests are way too hard, the model fails to learn and just resorts to reward hacking, basically trying to cheat the test. But if they're too easy, it just wastes computation. By constantly analyzing feedback, the proposer ensures tasks are calibrated right at that optimal success rate, maximizing genuine actual learning. But wait, what happens when the student masters the curriculum? Well, to prevent things from stagnating, the controller actively manages the library using 3 key moves. First, it refines existing skills using failure traces, basically fixing systematic errors. Second, it prunes obsolete or saturated skills. This is vital because stripping away the easy, trivial stuff saves an immense amount of computing power and keeps the AI totally focused. And crucially, third, it induces novel, brand new skills by extracting patterns from open-ended exploration. So the playbook is just constantly adapting to ensure maximum growth. Finally, Section 5, Pushing the Performance Frontier, the dramatic proof of concept. Okay, so does this theoretical framework actually work out in the real world? The answer is staggering. We're talking a 42.9 absolute point gain. The researchers tested this out on an initially weak, misaligned model called Ministral 38B on complex tool calling tasks. When they used unguided self-play, the model just completely stagnated. It couldn't even synthesize valid tasks to learn from. But when they brought skills self-play in to guide the process, boom, a massive 42.9 absolute point gain. It literally rescued the model from total failure. And it's not just some underdog story either. Across various open source models, this framework consistently pushes the performance ceiling. The larger 14 billion parameter mini-straws saw a very similar jump of 42.3 points. Even for models that were already highly competent straight out of the box, like QN38B, which started at a really strong 69.4, skills self-play still managed to squeeze out another 2.8 points of core capability. It proves the method scales brilliantly across totally different starting points. When you map out this performance footprint visually, it's pretty wild to see. Compared to the base model and even compared to unguided self-play, the model trained with skills self-play pushes the boundary outward in almost every single direction. It's vastly expanding capabilities far beyond what standard, unguided methods can ever achieve. And what's really exciting is that this success naturally transfers across domains. It is not just limited to tool calling. When they tested it on rigorous constraint satisfaction puzzles, specifically the really complex zebra logic benchmark, skill self-play yielded up to 12.0 absolute points gained overall. It created these striking turnarounds for logically weak models. It basically proved that ensuring structural accuracy in generated puzzles translates directly into advanced reliable logical deduction. That is a massive leap for creating AI tools that we can genuinely trust to solve complex problems. Which leaves us with this final thought to chew on. By implementing a dynamic skill library, we now have an incredibly reliable engine for AI self-evolution. So if AI can now autonomously build, verify, and continuously refine its own curriculum without just collapsing into useless noise, what are the actual limits to what it can teach itself? It is a total paradigm shift, and it opens up a truly sustainable, open-ended future for AI capability. Thanks so much for joining me on this explainer. I really hope this helped you clearly visualize exactly how the frontier of AI training is evolving right now.